Sudden stoppage of charge. Plane sheet moves on. Spherical sheet generated. Final result, the stationary field. 55. Having thus turned the radial isotropic displacement of the stationary charge into a traveling plane distribution, let us suddenly reduce the charge to rest. We know that after some time has elapsed, the former isotropic distribution will be reassumed, and now the question is, how will this take place? Let B in Figure 2 be the position of the charge at the moment of stoppage and after. Describe a sphere of radius v times t, with B for center. Then, the point C is where the charge would have got at time t after the stoppage had it not been stopped, and the plane DCE would have been the position of the plane electromagnetic sheet. Now, the actual state of things is described by saying that 1. The plane sheet DCE moves on quite unaltered, except at its core C, where the charge has been taken out. 2. The stationary radial displacement of the charge in its new position at B is fully established within the sphere, without any induction. 3. The internal displacement joins itself onto the external in the plane sheet over the spherical surface by leaking into it and then following the shortest route to the pole C. That is, the tangential displacement follows the lines of longitude. 4. The induction in the spherical sheet is oppositely directed to before, still, however, following the lines of latitude, and being connected with the tangential displacement by the former relations. In time, therefore, the plane sheet and the spherical sheet go out to infinity, and there is left behind simply the radial displacement of the stationary charge. 4. Medium moved instead of charge, or both moved with same relative velocity. 56. Now return to the case of 54, and referring to Figure 1, suppose it to be the charge that is kept at rest, whilst the medium is made to move bodily past it from right to left at speed v, so that the relative motion is the same as before. We must now suppose B to be at rest, the charge being there originally and remaining there, whilst it is A that is traveling from right to left, and the spherical surface has a motion compounded of expansion from the center A and translation with it. Attending to this, the former description applies exactly. The external displacement is continuously altering, and there is electric current to correspond, but there is no magnetic force except in the spherical sheet, and this is, as before said, accounted for by the motional magnetic force. The final result is now a stationary plane electromagnetic sheet, as, in fact, described before in 45, where we considered the displacement and induction in the sheet to be kept up steadily by electric and magnetic forces impressed by the motion. Now stop the motion of the medium without altering the position of the charge, and Figure 2 will show the growth of the radial stationary displacement as in 55, as it is in fact the same case precisely after the first moment. We can in a similar manner treat the cases of motion and stoppage of both charge and medium, provided the relative speed be always the speed v, however different from this may be the actual speeds. 5. Meeting of a pair of plane sheets with point sources, cancelment of charges, or else passage through one another, different results. Spherical sheet with two plane sheet appendages. 57. From the two solutions of 54, 55, either of which may be derived from the other, we may deduce a number of other interesting cases. Thus, let initially a pair of equal opposite charges plus rho and minus rho be moving towards one another, each at speed v through the medium, which for simplicity we may consider stationary, each with its accompanying plane electromagnetic sheet. When the charges meet, the two sheets coincide, the two displacements cancel, leaving none, and the two inductions add, doubling the induction. We have thus, momentarily, a mere sheet of induction. Now, if we can carry the charges through one another without change in their motion, the two sheets will immediately reappear and separate. That is, the plane waves will pass through one another as well as the charges. But if the charges cancel one another continuously after their first union, a fresh case arises. It is, given a certain plane sheet of induction initially, what becomes of it on the understanding that there is to be no electrification? The answer is that the induction sheet immediately splits into two plane electromagnetic sheets joined by a spherical sheet, as in Figure 3. For it is the same as the problem of stoppage in 55 with another equal charge of opposite kind moving the other way and stopped simultaneously, so that there is no electrification ever after. touching the sphere at the point F in Figure 2 is to be placed the additional plane wave, and the internal displacement is to be abolished. That is to say, in Figure 3 the displacement converges uniformly to F in the plane sheet there, then flows without leakage to the opposite pole C along the lines of longitude, and there diverges uniformly in the other plane sheet. Each displacement sheet has its corresponding coincident induction according to the former formulae. They all move out to infinity, leaving nothing behind, as there is no source left. 6. Spherical sheet without plane appendages produced by sudden jerking apart of opposite charges. 58. Similarly, let there be a pair of coincident or infinitely close opposite charges with no displacement, and let them be suddenly jerked apart, each moving at the speed of propagation of disturbances. The result is simply a single spherical wave without plane appendages and without leakage of the displacement. The charges are at opposite poles at the ends of the axis of motion, and the displacement just flows over the surface from one to the other symmetrically. There is the usual induction B equals mu v d0 to match. Figure 3 also shows this case if we leave out the plane sheets and suppose the positive charge to be at F and the negative at C. After a sufficient time, we have practically two widely separated plane electromagnetic sheets, although they are really portions of a large spherical sheet. Now, imagine the motion of the two charges to be reversed. If we simultaneously reverse the induction in the spherical sheet without altering the displacement, it will still be an electromagnetic sheet, but will contract instead of expanding. It will go on contracting to nothing when the charges meet. If they are then stopped, nothing more happens. But if the charges can separate again, the result is an expanding spherical electromagnetic sheet as before. 7. Collision of equal charges of same name. 59. If in the case of colliding plane sheets with charges 57, they be of the same name, then on meeting, it is the induction that vanishes, whilst the displacement is doubled. That is, we have momentarily a plane sheet of displacement that if the charges be kept together thereafter, this plane sheet splits into two plane electromagnetic sheets joined by a spherical sheet. At the center of the last is the doubled charge 2 rho, which sends its displacement isotropically to the surface of the sphere, where it is picked up and turned round towards one pole or the other. The equator of the sphere is the line of division of the oppositely flowing displacements. The displacement gets greater and greater as the poles are neared, the total amount reaching each pole being rho, half the central charge, which then diverges in the plane sheet touching the pole. The final result, when the waves have gone out to infinity, is, of course, merely the stationary field of the charge 2 rho. 8. Hemispherical sheet. Plane, conical, and cylindrical boundaries. 60. If a charge be initially in contact with a perfectly conducting plane, and be then suddenly jerked away from it at the speed v, the result is merely a hemispherical electromagnetic shell. The negative charge, corresponding to the moving point charge, expands in a circular ring upon the conducting plane, this ring being the equator of the complete sphere. This case, in fact, merely amounts to taking one half of the solution in 58 and then terminating the displacement normally upon a conductor. In Figure 4a is the original position of rho on the conducting plane CAE, and when the charge has reached B, the displacement terminates upon the plane in the circle DF. Instead of a plane conducting boundary, we may similarly have conical boundaries, internal and external, or on a conical boundary alone, with portions of perfect spherical waves running along them at the speed v. If the two conical boundaries have nearly the same angle, and this angle be small, we have a sort of concentric cable inner and outer conductor with dielectric between of continuously increasing thickness. The case of uniform thickness is included as an extreme case. The portion of the spherical wave then becomes a plane wave. General nature of electrified spherical electromagnetic sheet. 61. The nature of a spherical electromagnetic sheet expanding or contracting at speed v when it is charged in an arbitrary manner may also be readily seen by the foregoing. So far, when there has been electrification on the sheet, it has been a solitary point charge or else a pair at opposite poles. Now, the general case of an arbitrary distribution of electrification can be followed up from the case of a pair of charges not at opposite ends of a diameter, and each of these may be taken by itself by means of an opposite charge at the center or externally, so that integration docks the rest of the work. When there is a pair of equal charges of opposite sign, we do not need any external or internal complementary electrification, but we may make use of them argumentatively. Or we may let one charge leak outward, the other inward, and have the external and internal electrification in reality. The leakage should be of the isotropic character always, but the internal electrification need not be at the central point. It may be uniformly distributed upon a concentric sphere. This, again, may be stationary, or it may itself be in motion expanding or contracting at the speed v. The external electrification, too, may be on a concentric spherical surface, which may be in similar motion. The sheets, too, may be of finite depth and arbitrarily electrified, so that we have any volume distribution of electrification moving in space in radial lines to or from a center, accompanied by electromagnetic disturbances arranged in spherical sheets. There is thus a great variety of ways of making up problems of this character, the nature of whose solutions can be readily pictured mentally. Two charges, Q and Q2, for example, on a spherical sheet. One way is to put minus Q1 and minus Q2 at the center and superpose the two solutions. Or, the charges minus brackets Q1 and Q2 may be put externally with isotropic leakage. Or part may be inside and part outside. Or we may have no complementary electrification at all, but lead the displacement away into plane waves touching the sphere. Only when the total charge on the spherical sheet is zero can we dispense with these external aids, which to use depending upon the conditions of the problem. Then the displacement has sources and sinks on the sheet which balance one another. The corresponding induction is always perpendicular to the resultant tangential displacement and is given by the above formula, or B0 equals mu vector product VD0, where D0 is the tangential displacement in the sheet, volume density, depth. 1 case we may notice. If the density of electrification be uniform over the surface, there is no induction at all. That is, it is not an electromagnetic sheet, but only a sheet of electrification without tangential displacement and therefore without induction. So, with a condenser consisting of a pair of concentric shells uniformly electrified, either or both may expand or contract without magnetic force. This is, however, not peculiar to the case of motion at speed v. Any speed will do. But in general, if the speed be not exactly v, there result diffuse disturbances. The electromagnetic waves are no longer of the same pure type,